We're going to work some problems here to review for the semester final. This is the first video. We'll make another one later. So let's find the following limits. And here we have the limit as x approaches -3 from the left of 2 times x plus 3 over x plus 3. So a graph might help us see what's going on here. If we look at what's happening at -3, because if we direct substitute in -3, we're going to get 0 over 0, which is indeterminate. So if we plug in values of x that are less than -3, think like -5, -4, and get closer and closer. So if we plug in -5, -5 plus 3 is -2. The absolute value of -2 is +2. And we're going to get a -2 in the denominator. So that's going to be like a 2 times the absolute value. Let's write that as 2 times the absolute value of -2 over -2. If we plug in -4, we're going to get 2 times the absolute value of -1 over -1. And if we plug in something like, say, -3.1, we're going to get 2 times, and a -3.1 plus 3 is a -0.1, and we'll get a -0.1 in the denominator. So as you look at these, you'll see that this part of it, the absolute value of x plus 3 over x plus 3 is always going to be -1 when we are left of -3, and then that's going to get multiplied by 2, and so that's going to be a -2. So we're going to get something that looks like this. So as we get closer, as we work our way, going closer and closer to -3 from the left, this is going to be always a -2. Now as we come in from the right, so if you imagine plugging in numbers just to the right of 3, so imagine, or of a -3, imagine you plug in a -1. So if you plug in a -1, that's going to be -1 plus 3 is 2, and so we'll get 2 times 2 over 2. If we plug in a -2, we'll get 2 times, and -2 plus 3 is 1 over 1. If we plug in something like, say, a -2.9, we'll get 2 times 0.1 over 0.1. So we'll see this absolute value of x plus 3 over x plus 3 for all of these values is 1. That in turn is getting multiplied by the 2. So everywhere to the right, we're going to get just 2. And so our limit as we make our way closer and closer to -3 from the right is going to be a +2. So if our left-hand limit is -2 and our right-hand limit is +2, then our limit does not exist because the left-hand limit is different than the right-hand limit. Okay, let's look. I'm going to slide this up a little bit. Now this one, we can do a couple of ways. See if we can do this one without L'Hopital's rule. You could use L'Hopital, because if we direct substitute in 0, sine of 0 is 0, 0 times 3 is 0, and 5 times 0 is 0 in the denominator. So that's indeterminate. Indeterminate. So we could use L'Hopital's rule, but let's see if we can be a little more clever. If you remember the limit as x goes to 0 of sine of x over x is 1, then we could pull out the 3/5. That would make that sine 2x over x, still looking for the limit as x goes to 0. Now we need to make the denominator, the x in the denominator, be a 2x, so we'll multiply by 1 in a particular form. That's going to make this limit as x goes to 0 of There's our 3/5. Now we can borrow that 2 in the denominator to make our limit be what we want it to be. We've got that extra 2 left over there. Now, as x goes to 0, the sign of 2x over 2x goes to 1, times 3/5 times 2 is going to make our limit be 6/5. Now, on number 3, as x goes to 0, the inside part, this 1 over x, is going to go to infinity. So as x gets bigger and bigger and bigger, the sign just keeps bouncing back and forth between -1 and +1 and all those numbers in between. And so this will not get closer and closer to a single number. So we will say it does not exist because it oscillates. Oscillate. What am I trying to do here? Let me try that over again. So that's going to be oscillates. Lost where I was there. Okay, let me slide this up. Now this next one, we've not done one quite like this before. So as x gets really, really big, then x squared minus 4x, they're both getting big, but the x squared is getting much bigger, much faster. So that is looking like infinity minus infinity, which is indeterminate. Now, to resolve this one, we're going to do something kind of strange. We're going to multiply top and bottom by the conjugate. So I'm going to get rid of that arrow. So we're going to multiply top and bottom by the square root of x squared minus 4x plus x. And let's see what that does for us. So in the numerator, we're going to get the difference of 2 squares. So squaring the first term is going to get rid of the radical, and then squaring the second term is going to make that be a minus x squared, and the denominator is just going to stay what we put in there. Now we can see that the x squareds will kill each other off. We're taking the limit as x goes to infinity. So what happens, it's infinity over infinity, but if we think about this a little bit, we could try L'Hopital's rule, but we can say that as x goes to infinity, this x squared is going to dominate that minus 4x. So this is going to look like a negative 4x on top and a square root of x squared plus x in the denominator, which is going to look like a negative 4x over the absolute value of x plus x, which, since x is going to positive infinity, the absolute value doesn't matter because everything's positive here. So it's going to look like negative 4x over 2x, which is going to be negative 2. Kind of crazy. Okay, I'm going to slide this up. We want to verify that the intermediate value theorem applies to f of x equals 2 over x on the interval from 1 to 4, and find the value of c for which f of c equals 3. So the intermediate value theorem has to do with continuity. So we just have to argue that f is continuous on the interval from 1 to 4 because f is continuous everywhere. I'm going to say for all, everywhere except where it's going to be undefined. So for all x not equal to 0. So that's the only place where we have an issue. Now, I see I made a mistake here in my choice of f of c being equal to 3. So I'm going to change that real quick here. Let me say f of c is going to equal, let's say, 1. Because what we need to know is that our value that we're trying to find for f of c is in between f of 1 and f of 4. So f of 1 is going to be 2, and f of 4 is 2/4, which is 1/2. So we have that our 1 that we're looking for is in between 1/2 and 2. So we should be good to go now. So then what we're going to do is take our function 2 over x, we'll set that equal to 1, and because that's our k right here, and we're going to solve this for x. So if we multiply that x to the other side, then we're going to get that x equals 2. So our value for c is 2, and that will make our function equal to 1, and that is in our interval from 1 to 4. Okay, so the intermediate value theorem is a theorem about continuity. Let's see if we can do one of these huge graphs here. So we're going to sketch the graph of a function that satisfies these following conditions. So I'm going to read these across. I wrote these horizontally. So first we have that the limit as x goes to a positive infinity is -3. So that means we're going to have a horizontal asymptote to the right at y equals -3. And the limit as x goes to negative infinity is +1. So we're going to have a horizontal asymptote going to the left of y equals 1. We add the limit as x goes to -2 is from the left is going to be negative infinity. So that means we're going to get a vertical asymptote at x equals -2. And I'm going to make a little note to myself that we're going to go down to negative infinity on the left side. The limit as we approach -2 from the right is positive infinity. So that means our vertical asymptote on the right side is going to be up over here. On the second row, the limit as we approach 0 from the left is -2. So that means as we approach 0 from the left, I'm going to put a little tail on the left side, we're going to approach -2. As we approach 0 from the right, we're going to approach +1, and f of 0 is 1. So I'm going to put f of 0, I'm going to make the graph be in green. So that's a point that's actually on our curve. Now to the third row, the limit as we approach 2 from the left is negative infinity. So we're going to have a vertical asymptote there at x equals 2. And the limit as we approach 2 from the right is also negative infinity. So it's also going to go down on the right side. As we approach 4, the limit is going to be 2. So that's going to be on both sides. So I'm going to put a tail on both sides. And the actual function is undefined there, so we'll just leave it blank. There will be no point that has an x-coordinate 4. All right, let's see what we got here. We know it's going to approach our horizontal asymptote, and the next thing I see is this arrow going down, so it's going to do something like that. At least that's the conservative way of drawing that. On the other side, we're going to hop over the vertical asymptote and come up here, and then we're going to approach our value at x equals 0. We're going to approach -2 from the left. The function's actually going to be 1, and then we're going to go off to the right. Looks like we're going to drop down and go to negative infinity on the left side, also to negative infinity on the right side, and approach a y value of 2 at an x value of 4, and then we're going to approach that horizontal asymptote to the far right. There is a possible graph. Okay, let's slide up and see if we can find f prime of a using the definition of the derivative given by f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. Our function is going to be 1 over x minus 3, and the value of a is 5. So we're going to take the limit as x approaches a, which our a is going to be 5. So the limit as x approaches 5 of f of x, which is going to be 1 over x minus 3, minus, and f of a is going to be 1 over 5 minus 3, and that's going to all be over x minus 5. Okay, so let's see what we can do with this. We're going to take the limit as x approaches 5. We need a common denominator here. Well, let's see. Maybe I'll simplify that a little bit first. We have 1 over x minus 3 minus 1/2 all over x minus 5. So that's going to be the limit as x approaches 5. We need a common denominator, so we're going to multiply top and bottom by 2 on the first one, and we're going to multiply top and bottom by x minus 3 on the second fraction. That's all going to be over x minus 5. So let's see, we're going to get the limit as x approaches 5. In the numerator, that's going to be 2 minus x plus 3 all over 2 times x minus 3. And this is going to be 2 divided by x minus 5 is going to be 1 over x minus 5 when we're ready for it. So let's see, that's going to be the limit as x approaches 5. So when we combine, that's going to be a 5 minus x over 2 times x minus 3 times 1 over x minus 5. So if you remember, 5 minus x and x minus 5 will cancel, but leave a negative 1. And so now when we take that limit as x approaches 5, we're going to get negative 1 on top. We'll get 2 times 5 minus 3 on the bottom. So that's going to be negative 1 over 2 times 2 is 4, and that is our limit. Okay, let's slide up. Let's see if we can find an equation of the normal line to y equals tangent 2x at x equals pi over 6. So remember, a normal line is perpendicular to the tangent line. So we need a point. So the x value is pi over 6. So our y value is going to be f of pi over 6. That means we're going to take the tangent of 2 times pi over 6 is going to be pi over 3. So I guess we're going to have to take the sine of pi over 3 over the cosine of pi over 3. Sine of pi over 3 is going to be square root of 3 over 2. Cosine of pi over 3 is 1/2. That's going to get us to square root of 3. So that's the y coordinate. So our point on this tangent line and normal line is going to be pi over 6 for the x coordinate, square root of 3 for the y coordinate. So now we need the slope. Well, the slope is going to come from the derivative. This is a chain rule derivative, so we're going to get secant squared of 2x times the derivative of 2x. We want to, for our slope, get the derivative evaluated at pi over 6. So that's going to be 2 times, let's see, secant squared is going to be 1 over cosine squared of 2 times pi over 6 is going to be pi over 3. So let's see, that's 2 times, and the cosine of pi over 3 is 1/2, and we're going to square that. So that's going to be 2 over 1/4, and to multiply by the reciprocal is going to make that be an 8. So the slope of our tangent line is 8. So that means that the slope of the normal line, the line perpendicular to that, will be the negative reciprocal. So that's going to make our normal line. So our normal line is going to be y minus the square root of 3. will equal our slope, which was perpendicular to the tangent line, negative 1/8 times x minus pi over 6. There we go. Okay, let's slide up here a little bit and see if we can find the absolute maximum and the absolute minimum for our function f of x equals 1 over x plus 4x on the closed interval from 1 to 4, and we want to justify our answer. So our EVT, the extreme value theorem, says that a continuous function on a closed interval domain must have an absolute maximum and an absolute minimum. Our function f is continuous everywhere except for 0, so on our closed interval domain 1 to 4, we should get both an absolute max and an absolute min. So we're going to use what we call the candidate test, and this is going to be our justification. So we're going to take the derivative, f prime. So let's see, the derivative of x to the negative 1 is going to be negative x to the negative 2. The derivative of 4x is 4, so that's going to be negative 1 over x squared plus 4. We want to set that equal to 0 and solve it to look for any critical points. So I'm going to add the 1 over x squared to the other side. We can take the reciprocal of both sides and get 1/4 equals x squared. If we take the square root of both sides, we're going to get a positive and a negative 1/2. Now we also have a critical point of 0 because that will make our derivative undefined. So these are our critical points. But our domain is only from 1 to 4, so none of these critical points are on that domain. So all we need to do now is to evaluate the endpoints. And the largest of these values will be our maximum, and the smallest will be our minimum. So if we plug in 1, we're going to get 1 over 1 plus 4 times 1. That's going to be 5. If we plug in 4, we're going to get 1/4 times 4 times 4. That's 16 and 1/4. So this is the absolute maximum. Remember, that's a y value. And this is the absolute minimum. That also is a y value. And it has been justified because of our work, because we have shown the candidate test. So we don't have to add any words or sentences there. Okay, this is a tough one. So this is off of our Miss Brown optimization worksheet. Penelope wants to get the largest rectangular pool that will fit in her backyard that's bounded by y equals negative 1/2 x squared plus 5 and y equals negative 3. Let's see if we can see what this is going to look like. So y equals negative 3 is going to be this horizontal line over here. Now, negative 1/2 x squared plus 5, we know is going to have a vertex at 0, 5 up here, and it's going to be a parabola that opens down. And so it's going to look something like this. And we kind of need to know what these points are right here to know what our boundaries are, because we are going to try to imagine putting the biggest rectangular pool that we can in this strange looking backyard that Penelope has. So let's see, we need to find these values. That's going to be where our function negative 1/2 x squared plus 5 is equal to that negative 3. So I think I'll add the 1/2 x squared to the right side and add the 3 to the left side, then multiply by 2, and it looks like when we solve this that we're going to get that x can be negative 4 or positive 4. So that's telling us what these boundaries are right here. So right there is going to be our negative 4 and our 4. Now, this point right here is a shared point with our rectangular pool and our curve. So it's going to be x for the x-coordinate, and its y-coordinate is going to be negative 1/2 x squared plus 5 because it's on that parabola. Now our rectangle, we're trying to maximize its area, and that is going to be the base times the height. So our base is going to be this distance right here, which we can see if we compare it to this x value right there, that our base is going to be 2x. Our height is going to be this distance right here, and we can see that's going to go from here to here. So this much of it that takes us to the x-axis is the y-coordinate of this point, and then this distance is down to -3. So if we take the top point minus the bottom point, that is our negative 1/2 x squared plus 5 minus that -3, that's going to be negative 1/2 x squared plus 8, or I'm going to write that as 8 minus 1/2 x squared. That is going to be our height, 8 minus 1/2 x squared. Okay, well, I think we want to distribute that 2x before we take our derivative. So that's going to be 16x minus, and then the 2 and the 1/2 will cancel, and we'll get an x cubed. Remember, we're looking for the maximum area, the dimensions of the pool that will have the maximum area. So we need the derivative of the area. That's going to be 16 minus 3x squared. We want to set that equal to 0 to find the critical points. So that's going to give us 16 equals 3x squared. 16 thirds is equal to x squared. X is equal to a plus or minus square root of 16 thirds, which is a plus or minus 4 over square root of 3. Well, we probably better think about what is a reasonable domain here. So let's look at our picture here, because we can make our life easier by making an efficient domain. Now remember that our base is given by this 2x right here. So since a base of a rectangle can't be negative, then we could say that certainly the x has to be bigger than 0. It's also got to fit inside of this little region in our backyard there, which has a largest x value of 4. Now, whether it could actually be 4 or 0 is maybe a little bit of a philosophical discussion. If x was equal to 0, it would tell us that we have a base of 0. I don't really think that's going to be much of a swimming pool. And likewise, if x was 4, we'd have a height of 0. And so I kind of think we probably should stick with the strict inequalities, which is unfortunate because that means we can't use our candidate test. But we're going to be okay because we only are going to have one critical point on this domain, and that's going to be the positive 4 over the square root of 3. So if we plug in something to the left of 4 square root of 3, and we're trying to look at our derivative here, so we're turning our attention to this. If we take something less than 4 over square root of 3, maybe something like 1, then 16 minus 3 is going to be positive. And if we take something bigger than that, something closer to 4, like maybe 3, then 3 squared is 9 times 3 is 27, and we're going to get 16 minus 27 will be negative. So now we can say that that our area, A, has a relative maximum at x equals 4 over the square root of 3, because A prime changes from positive to negative, period. V of 4 square root of 3 is the maximum, or the absolute maximum, because it is the only critical point on the domain. So we have made our argument, and if we need our dimensions, then we need to say that our base is going to be right here. So our base will be 2 times that 4 over square root of 3. So that's going to be 8 over square root of 3. And our height is going to be the 8 minus 1/2 times 4 square root of 3 squared. So that's going to be 8 minus, so that's going to be 1/2 times 4 squared is 16. Square root of 3 squared is 3. We can cancel, and so that's going to be 8 minus, I guess that's going to be 8/3. So since 8 is 24/3, that's going to be 24/3 minus 8/3 is 16/3, I think. So that's going to be our height. So we have our dimensions, our base and height of that rectangle. That's what our pool is going to have for a base and height. Okay. So let's look at our last one here. Water is leaking out of a tank that is an inverted cone. So it's going to look something like this. And it's got a radius of 6 feet. And it's got a height of 10 feet. So there are the dimensions of our cone. How fast and is leaking out? So it's leaking out at 3 cubic feet per hour. So we have water inside here, and it's going to take the shape of a cone because water takes the shape of whatever it's sitting in. And the fact that it's leaving at 3 cubic feet per hour means that dV dt is a -3. So the volume is decreasing. We want to know how fast is the water level dropping. So that means we're looking for a dH dt. When the water in the tank is 4 feet deep, that means when the H is equal to 4. So we have some similar triangles here. We have the triangle that comes from the actual tank itself, and we have the triangle of water inside there. Now the tank is fixed. Its radius is 6 and its height is 10, but the radius and the height of that water, that triangle of water, is changing with time. But they are similar triangles, which means their sides are proportional. So R over H is going to equal 6 over 10, which means that R is going to be 6 over 10 times H, or if we reduce, we can make the numbers a little nicer and say R is 3/5 H. So the volume of a cone is 1/3 pi R squared H. So our cone is going to be 1/3 pi, and we're going to replace that R by 3/5 H, square that, and then times the other H. So that looks like one of the 3's in the 1/3 and one of the 3's in the 3 squared can cancel. So we'll still have the extra 3 over 25, 3 pi over 25, and then we're going to get an H cubed out of that. Now we can differentiate with respect to t. So we'll get dV dt is going to be, the 3 is going to multiply that 3 pi over 25 and become 9 pi over 25 h to the second times dH dt, the derivative of that height. Our height, or the dV dt rather, we said was a -3. So that's going to be -3 is 9/25. The h we said was 4 squared times the dH dt. This is not going to be pretty. So we've got negative 3. That's going to be, 4 squared is 16. 9 times 16 is 144. I think I left the pi off there. Pi over 25 times dh dt. So if we come up here, we'll get our dh dt is going to be that negative 3 times 25 over 144 pi. 3 goes into 144. What is that? Let's see. That's 48 pi. I think that's going to be 48. So I think we get our dh dt is going to be a negative 25 over 48 pi, and our units there are going to be in feet per hour. All right, that's a little bit of practice for our final review, for our final exam.